My name is Austin Poncelet, for those of you that don't know me. I'm a master's student here at Cal State Fullerton, studying geology under my wonderful thesis advisor, Dr. Adam Woods. Today I will be talking about the timing, consequences, and nature of the late Ordovician glaciation using the Ely Springs Dolomite of East Central California. So overall, what is the late Ordovician glaciation? Well, it's an anomalous glacial episode that occurred about 445 million years ago. If we look here at our Phanerozoic timeline, moving from the Cambrian to present day, again about 542 million years, and we look across our Ordovician Silurian boundary, we can see that CO2 levels, denoted by this orange, green, and blue line, are about 10 to 16 times greater than present levels. It was also a glaciation that had significant impacts on Earth's biota, specifically causing the extinction of about 61% of marine genera. It was also the first glaciation of the Phanerozoic. So if we look here across our Phanerozoic timeline, moving from the Cambrian to present day, so we've sort of flip-flopped our timeline here, and we look across the Ordovician Silurian boundary, we note this first blue rectangle, or the first glaciation of the Phanerozoic, that coincides with also elevated delta O18 values. It's also a glaciation that's timing in nature is still very much poorly understood. And so Adam and I were hoping to tackle that a bit in our study. So overall, what is the evidence of glaciation? Well, first and foremost are glacial tilllights. Here we have an example of a glacial tillite seen from northern Norway. And this is a modern day glacial tillite. But essentially what glacial tilllights are just the sediments that are deposited by glaciers. As glaciers form and move, they erode down into the bedrock beneath, picking up sediment and rock fragment. Eventually, as they melt, they deposit these sediments, as we see here between this quartzite, this tan unit here, above it, the glacial tillite. We see these all over North Africa in the late Ordovician, and so we assume that there was some glaciation at this time. However, it's been poorly constrained with these glacial tilllights and requires further study. These glacial tilllights also coincide with positive delta C13 and delta O18 values. We're more interested in looking at the delta C13 because that's what we'll be looking at in our study with the Dolomites of the Ely Springs. So how do we get glaciation when we have CO2 levels that are 10 to 16 times greater than present? That would seem anomalous. Well, Brenchley et al. In 1994 is looking at the late Ordovician world. He's seen Gondwana, or present-day North Africa, moving northward across the South Pole. As we do this, temperatures are going to decrease to the point where we will get the development of snow and ice sheets. When this happens, we're going to increase our albedo effect. When we increase the albedo effect, we're moving more heat and light away from Earth's surface. Eventually, this will create a positive feedback loop until we get glaciation. So Kump et al. In 1999 is thinking something a little different. He's looking at the late Ordovician world, and he's not so interested in Gondwana moving northward across the South Pole, as he's the Taconic orogeny occurring on the eastern margin of Laurentia here. The Taconic orogeny, or formation of the Appalachian Mountains, is important because during a mountain building event, we're increasing the steepness of our terrain. When we do that, we'll increase the erodibility or weatherability of our rocks. This is important as it relates to silicate weathering equation. Here, we're taking silicate rocks and eroding them, which is ultimately pulling down CO2 from the atmosphere to make bicarbonate. Eventually, as we pull more and more CO2 down through this Taconic orogeny, we'll get the development of snow and ice sheets. We'll get a higher albedo effect, ultimately leading to glaciation. So now looking at the hypotheses that go along with the timing of glaciation. We have three main periods in the upper or late Ordovician. We have the Sambian, the Cadian, the Hernantian, and we're just looking at one period in the early Silurian, the Rudanian. So let's look at these time periods. The Sambian is just 2.4 million years long. And we're not so interested in it because there's really no hypotheses stating that glaciation occurred that far back. So looking now at the Cadian, we see that it's 11 million years long, and the Hernantian's about 1 million years long. So let's look at the hypotheses first that start with the 1 million year long glaciation confined to the Hernanchen. These studies that advocate for a short glacial period of about 1 million years would be Finnegan et al. In 2011 and Brenchley et al. In 1994. Finnegan et al. In 2011 looked at carbonate clumped isotope paleothermometry throughout the late Ordovician and noticed sea surface temperatures in the range of about 32 to 37 degrees Celsius. However, if we look here in the Hernanchen, we can see that sea surface temperatures dip to about 27 to 28 degrees Celsius. And they note that this drop in sea surface temperatures is most likely glacially induced, again constrained to that short 1 million year time period of the Hernanchen. Brenchley et al. In 1994 looked at eight different studies to compose bathymetric curves. They note a sharp decline or decrease in sea levels that's confined to the Hernanchen or that 1 million year time period. And in fact, that sea levels were probably rising before that. Now looking at the 11 million year time span for glaciation, or that would be starting in the earliest Cadian and moving up through the Hernanchen. The advocates for this longer period of glaciation are Saltzman and Young, 2005, and Pope and Steffen in 2003. First, looking at Saltzman and Young's study, they looked at the Copenhagen Formation and Antelope Valley limestone within the middle to early late Ordovician, specifically looking at the delta C13 values. They weren't so interested here in the upper late Ordovician because the Hernanchen isotopic carbon excursion is globally known. So they want to know what's happening before that. In the Mohacian or the Chatfieldian, we can see that we have an early on Chatfieldian excursion, which they attribute to an early on glaciation occurring here, or the Chatfieldian, which is analogous to the earliest Cadian. So again, advocating for this long glacial period. And lastly, Pope and Steffen in 2003 looked at the Montoya group of Texas, New Mexico, and Oklahoma. They noticed in their study an abundance of chert and phosphates that they attribute to increased upwelling. They attribute this upwelling to increased thermohaline circulation via glaciation across Gondwana. Ultimately, these chert and phosphates were deposited across the earliest late Ordovician, again indicating that we would have glaciation and the onset of upwelling starting here at the Cadian and moving its way up through the Hernanchen. So we have Finnegan et al. In 2011 and Brenchley et al. In 1994 saying that glaciation is about 1 million years long and confined to the Hernanchen. And then we have Saltzman and Young in 2005 and Pope and Steffen in 2003 saying that glaciation was about 11 to 13 million years long and starting in the earliest Cadian and up through the Hernanchen. So this puts us in a bit of a predicament. Okay, but luckily we have the Ely Springs Dolomite, which just happens to be conveniently deposited across the Cadian, Hernanchen, and up through the early Silurian. The Ely Springs Dolomite can tell us about the timing and nature of glaciation throughout the late Ordovician by first looking at the lithology. The lithology of the Ely Springs Dolomite is going to tell us about sea surface temperatures and the depositional environments that occur within the Ely Springs Dolomite. We could then use the lithology to create a sequence stratigraphic model to understand how sea levels were changing throughout this time. We then looked at delta C13 data at both the hard scramble nose and NOPA range. We can compare then our delta C13 data to that of the global curve to understand how our lithology matches up with the timeline of the late Ordovician and the early Silurian. And lastly, we can look at trace element data within the Ely Springs Dolomite to understand productivity, diagenesis, and detrital input. Our data collection for this study was fairly straightforward. We spent about 3 days at each study locality of the hard scramble nose and the NOPA range. At each field site, we collected samples every 1.5 meters. We then used our field observations and the samples collected to create our sequence stratigraphic model. We then used these samples collected every 1.5 meters to analyze delta C13 values in Dr. Sean Lloyd's lab using the cavity ring down spectrometer. We then use these samples collected every 1.5 meters from hardscramble nose specifically using Dr. Adam Wood's ICP OES. So the Ely Springs dolomite will tell us about glaciation, but it will give us we have a few hypotheses as to how long or what glaciation was doing throughout the late Ordovician. And this relates to the Ely Springs dolomite by its sequence stratigraphic evidence and its sedimentological evidence. So our first hypothesis would be that we have a long-term glacial period. In this case, we would expect to see large 10 to 25 meter sea level fluctuations occurring throughout the Cottian and up through the Hernanchen. We would expect these large sea level fluctuations because we'd have extensive glaciation starting here, which would be locking up seawater and decreasing sea levels throughout this 11 million year time span. We'd also expect to see the heterozoan carbonate grain assemblage, which are basically just cool water carbonates. These are dominated by skeletal grains, which we see in this modern thin section, which we have bryozoans and foraminifera. We'd expect to see this heterozoan carbonate grain assemblage, or cool water carbonates, throughout the entirety of the Cottian and up through the Hernanchen, as we'd have glaciation throughout this entire period. Our next hypothesis is just the opposite, is that we'd have a short glacial period. So what we would expect to see here are small, less than 10 meter sea level fluctuations occurring throughout the Cottian, and then large 10 to 25 meter sea level fluctuations throughout the Hernanchen, where we would have the apex of glaciation. We'd also expect to see the photozoan lithologic or carbonate grain assemblage. The photozoan and the carbonate grain assemblage just means we have warm water carbonates. We would see this occurring throughout most of the Cottian as we'd have warm water before glaciation. We then expect to see in this Hernanchen period only the heterozoan carbonate or cool water carbonate grains. The photozoan lithologic or carbonate grain assemblage would look something like this. This is an example of thin section from the Ely Springs dolomite. Note that this thin section is a little blurry because we have the replacement of primary calcite with secondary dolomite. We can see several non-skeletal grains in this thin section. We have a Gervinella oncoid here at the bottom right-hand side of the thin section, a bacterial mat here at the top, and confined within this red rectangle we have some peloids, which are thin tan ellipsoid shapes, but are also scattered throughout this entire thin section within the light matrix. The third hypothesis would be that we have a long-term global cooling. So in this case, we don't have long-term glaciation, just a cooling period with a short glacial period. In this case, we'd expect to see evidence of cooling throughout the Cottian and becoming the most cold when we have the apex of glaciation in the Hernanchen. Here we would expect small, less than 10 meter sea level fluctuations, grading up into larger 10 to 25 meter sea level fluctuations throughout the Cottian and as we approach the Hernanchen. We'd also expect to see the photozoan carbonate grain assemblage, or warm water carbonates, grade upwards into the heterozoan carbonate grain assemblage as we move towards the Hernanchen. So let's take a look now at our actual study localities. We have the hardscramble nose on the edge of this middle to inner carbonate ramp depositional environment. We have the Nopah range, which is situated in this more inner carbonate ramp depositional environment. If we look at the late Ordovician world, our study localities would be located where this star is, or on the western margin of Laurentia. In Google Earth view, the hardscramble nose is confined, or our study locality is confined within this red rectangle. If you move in the direction of this arrow, you're moving from the bottom or the base of the unit to the top of the unit, as we see here in this column. Now looking at the Nopah range. In Google Earth view, our study locality is confined by this red rectangle. When you move upwards in the direction of this arrow, you're moving from the base of the unit or the locality to the top of the locality. So now let's take a look at our actual lithology and sequence stratigraphy. Starting with hardscramble nose, in this relatively deeper water environment to that of the Nopal Range. First, looking at the contact between the Eureka quartzite here, which is this light tan quartzite indicated by the red arrow, and the Ely Springs dolomite here in the top left-hand corner. We can see this contact nicely in the Google Earth view between the Eureka quartzite, which is this light tan unit here, and then this is the contact between the Ely Springs dolomite, which is this medium to dark gray unit that I'm circling with my pointer. Upon initial inspection of the Ely Springs dolomite, we can see in thin section that it's dominated by peloids, or the photozoan carbonate grain assemblage, indicating that we have mostly warm waters at the base of our unit here. There are some skeletal grains, as we can see here, by crinoid columnal, but because there's just a dominance of non-skeletal grains, we can consider it to be photozoan. Moving slightly upwards now at the hard scramble nose to about 1 meter, we can see mud rip-up clasts here of the Eureka quartzite that are incorporated within the Ely Springs dolomite. This is ultimately telling us that we're in some higher energy environment. In this case, we probably have storm events that are ripping up into the Eureka quartzite and eroding down into it and mixing up fragments into the Ely Springs dolomite, as we can see in this photo. Moving a bit upwards now to about 10 meters at the Ely Springs dolomite, we start to see the influence of chert. This chert, which are these black units or beds that move horizontally across the formation, become nodular, as you can see here where I'm pointing, to bedded as you move upwards. This is important because it means we're rising in sea level. And we note that we're rising in sea level because silicification is much easier under relatively cooler, deeper water environments. We can see here in thin section that the Ely Springs dolomite is still dominated by the photozoan carbonate grain assemblage, or is dominated by peloids. In this case, we're still under warm waters. To about 25 meters now, we see a dark, medium to dark gray, skeletal-rich dolopaxstone. We see a bivalve fragment here, a rugose coral, and a crinoid columnal. Now, you'd be telling me that Austin, we're seeing a lot of skeletal grains within our carbonate, and we must be in cool water now. But if we just move a bit further up to about 31, 32 meters, we can still see that our lithology is predominantly of the photozoan carbonate grain assemblage. Again, here we're seeing our Gervinella oncoid, bacterial mat at the top, and abundant peloids scattered throughout, essentially telling us that we're still in warm waters. Now moving over to the shallower Nopal Range setting. So this is the base of the Nopal Range locality. When we look at it in the Google Earth setting, there's no bedded units of the Eureka quartzite here. As you can see, the gray is sort of mottled with that light tan, which is indicating that we don't have any bedded units. And therefore, the first bedded unit that we see of the Ely Springs dolomite is considered to be our base or contact. So it's sort of inferred. Looking a little closer now at this photo, or the lithology, we notice that the Ely Springs dolomite is a medium to light gray dolopaxstone with abundant crinoid columnals, as you can see these little white specks throughout. When we move upwards, we can see that the lithology becomes even more fossiliferous here. However, these skeletal grains are associated with warm waters, specifically looking at this tabulate coral, bacterial laminations here in the top left-hand corner, and a stromatolite head indicated by this green arrow. At around 22 to 23 meters, we start to see the influence of chert, just like we did at hard scramble nose. This is telling us now again that we're seeing an increase in sea level as we move from nodular chert at the base to bedded chert towards the top. Here in this red circle or ellipse, we can see a lithistid sponge, which accounts for most of the chert production in the Ely Springs dolomite. So what does this overall tell us about both units when we look at Unit 1 and Unit 2 of the lower member? Well, it probably tells us that we're in transgressive systems track 1, and 1 just denotes the first one that we see in the sequence. This means that we're going to rise in sea level, Again, we're rising in sea level because we're seeing these chert beds increase in thickness throughout the study localities. When we do this, we're going to move the depositional environments of the Nopah Range and hard scramble nose down ramp. So essentially what's happening is we're taking this medium to dark gray dolowaxstone and we're moving it to now this dark gray dolowaxstone to dolopaxstone with about 20% of chert by volume. We can see this reflected here in our stratigraphic columns. It's then capped by what we interpret to be our maximum flooding surface, or to where we see the thickest chert beds. Looking above the maximum flooding surface now at hard scramble nose, we see a light to medium gray dolowaxstone to dolomudstone with abundant chondrites burrows and potentially some bacterial laminae down here at the bottom. We can see these chondrites burrows very nicely in thin section. However, the main point here is that we're still seeing the photozoan carbonate grain assemblage, or warm waters, dominated by peloids. Around the same stratigraphic height, we see this light gray dolomudstone with these chert nodules that have this distinct shape. Note that these nodules are now not bedded and we're not seeing any chert beds anymore. These chert nodules have a specific shape, basically in the form of sponge colonies, which we interpret to be lithostid sponges, and again account for most of the chert production across both localities. Looking now at the Nopah Range above the maximum flooding surface, we're seeing these 5-meter packages or cycles. So let's take a look at what the lithology of one of those 5-meter packages would look like. At the base of one of these 5-meter cycles, we're seeing a light to medium gray skeletal dolopaxstone with some remnants of chert, as you can see here by these tiny little tan to brown specks. And that's because we're at the top of one of those lithologies. This is then grading into an oncoid shoal. We can see those oncoids nicely here within the red ellipses. We can see those nice concentric laminae of the oncoids and note how massive they are, and we don't even need to see them in thin section. Moving a bit upwards above that oncoid shoal, we move into a brecciated horizon of about 1 meter thick. This brecciated horizon is important because it means that we've subaerially exposed our carbonate ramp, or moved sea levels down beyond Nopah Range to where there's no longer carbonate deposition occurring. However, since we're seeing these packages reoccur, it means that sea level is moving up and down within Nopah Range. But note that hard scramble nose is not really seeing any brecciation at this point. So now looking at both study localities, we see about the same lithology. Here we're looking at 10-meter thick units of brecciation that have been chaotically arranged. These breccias that are about 10 meters thick indicate our highest extent of sea level fall. And they correlate across because we're not seeing any carbonate deposition as sea level has fallen beneath both Nopah Range and hard scramble nose at this point. Across or within these red brackets, we even have a little red to pink stripe or bed, which indicates that we probably have some sort of paleosol or terra rosa. Ultimately, this indicates that above the maximum flooding surface, we're seeing the high stand systems track 1, or an overall shallowing in sea level. So what's happening here is below these breccias, we're having some carbonate deposition still as sea levels fall. So hard scramble nose and Nopah Range are still depositing carbonates. However, as we move sea levels down even further, eventually hard scramble nose and Nopah Range will be in this brecciated horizon. This means that we have, again, our highest extent of sea level fall. These breccias are interpreted to be our sequence boundary, or the point to which that we note that sea levels have fallen to their greatest extent. Above the sequence boundary at hard scramble nose, we see the redeposition of carbonates, or this medium to dark gray dolopaxstone above that breccia. This means that now we're rising sea levels above hard scramble nose to the point that we can now get deposition. However, moving just a bit upwards above that bedded dolopaxstone here, we're seeing breccias again. However, this breccia looks much more different in nature than those chaotic or 10-meter thick breccias we saw around our sequence boundary. instead of being chaotically arranged, it's a mosaic breccia, and we can still see some of its original bedding here. This means that we haven't had as substantial subaerial exposure. Wow, that's annoying. So overall, the lithologies and hard scramble nose are telling us that we're in the low stand systems track 1. This means that as we move sea levels up after the sequence boundary, we're getting some deposition of the dolopaxtones here. Subsequently, we'll move sea levels down again, so we'll move hard scramble nose into this brecciated horizon. This ultimately means that we're seeing a 2-pulse glacial cycle. Note that we're not recording any of this 2-pulse glacial cycle at no-paw range because we don't see any redeposition of dolomites above the sequence boundary. So sea level hasn't gotten back up to the no-paw range yet, but is still shifting around the hard scramble nose. Transgressive surface where we end the low stand systems tract. We note in the hard scramble nose the return of bedded medium to dark gray dolopaxtones with chert nodules and I think some chert beds which are a little lower in the unit. And then at no-paw range, or the shallower water setting, we're again seeing the return of light to medium gray dolopaxtones to dolowaxtones with again a return to chert beds and some chert nodules. Ultimately indicating that we're now on transgressive systems track 2, or now the rise of sea level, and we're depositing dolopaxtones or dolomites at hard scramble nose and no-paw range. Whoa, so that's a lot, and so I just want to sum it up. So essentially what we're seeing at the base of both localities are deep chert-rich peloidal dolopaxtones that are accompanied by high-frequency small-scale autocycles. This means that we have rising sea levels under warm conditions and high CO2 levels, indicating we're in transgressive systems track 1. Above this maximum flooding surface, we're then seeing relatively shallow, chert-poor, bioturbated mudstones, which indicate that we have steadily declining sea levels, and are also accompanied by high-frequency small-scale autocycles of less than 10 meters. This indicates we're in high stand systems track 1 throughout these bedded dolomites here. When we get to our chaotic, heavily rotated breccias, it means we have our highest extent of sea level fall and surface exposure. It's a low-frequency, large-scale fluctuation and is therefore associated with glaciation. And it also indicates our sequence boundary. When we move back into bedded medium to dark gray, chert-rich dolopaxtones that are accompanied by small-scale, low-frequency autocycles, it means that we're now rising in sea level after the apex of glaciation and our highest extent of sea level fall. So now looking at our Delta C13 data. So why do we even care about the Delta C13 data when we've already looked at the Ely Springs Dolomite and have some idea as to what glaciation is doing throughout the lithology? Well, if we can create a curve for the hard scramble nose and no-paw range, then we can compare it to that of the global Delta C13 curve. It's useful because if we can understand where the Heiss or Hernantian isotopic carbon excursion is, then we can correlate our spike with that of the Heiss and interpret that to be the Hernantian, and to see if our lithology would match up with something of that that would be indicative of glaciation. So our maximum at hard scramble nose is just 0.57 per mil at 56 meters. Our maximum at no-paw range is 1.47 per mil at 58 meters. So when we look at both curves and compare it to that of the global Delta C13 curve, and we note the Heiss here, then we can interpret that our maximum values are probably the Hernantian isotopic carbon excursion here as well, and also match up nicely with our breccias, or our highest extent of sea level fall due to glaciation. However, there's just one problem, and that's that our values are pretty much about half that we see here in the global Delta C13 curve, where you have 1.47 per mil, which is our highest at no-paw range, and just 0.57 at hard scramble nose. And this compares to the 3 to 8 per mil excursion seen here in that global curve by Saltzman and Young and Kump et al. In 1999. So why is the height so diminished here for the Ely Springs dolomite? Well, there's two things that could advocate for the reduced spike here that we're seeing. And that first off could be that we have non-deposition or erosion of our lithologies due to subaerial exposure and glaciation. So essentially, the lithologies that would contain this data never actually got deposited or have been eroded down into. And therefore, we wouldn't have actually collected any of that data. Secondly, the replacement of primary calcite with secondary dolomite has shown a greatly reduced delta C13 values. And thirdly, carbonates deposited in epieric seas have been shown to have greater delta C13 values, like that seen in Saltzman and Young and Kump et al. In 1999. And that's because they have an overall smaller dissolved inorganic carbon pool. So any carbon introduced to the system there will have a much greater effect. The next thing we notice that's sort of anomalous is that the Nopah range seems to be higher for the Heiss than the hardscramble nose, where again we have a maximum of 0.57 per mil at hardscramble nose and 1.47 per mil at Nopah range. Well, this could be due to the jumbled nature of the breccias and ultimately just faulty sampling. So when you have breccias, you have those clasts that have been rotated and moved around. So essentially, what class could have contained the values such as 1.47 within the Ely Springs dolomite were essentially just not collected or sampled. And secondly, the Nopah range is a more lagoonal or shallower water setting. At the Nopah range, you'll have more productivity and more carbon burial, which will ultimately drive that delta C13 spike upwards. Now moving in or transitioning to our trace element data. First, we looked at productivity, which relates to barium. Barium is the element found in marine biological debris. So from the base of the unit of the from the base of the hardscramble nose to about halfway up through unit 2 of the lower member, we see a general decrease in barium values from 12.7 parts per million to 0.87 parts per million. This decrease in barium coincides nicely with these chert beds or our rising sea levels under warm, sluggish conditions. Here we wouldn't expect to see large increases in productivity because we wouldn't have any glaciation to create that upwelling and delivering nutrients to the surface. It's not until 50.5 meters that we see the spike in barium at 33.3 parts per million. This matches up nicely with the base of our breccia here, and also the apex of glaciation, the point at which we would expect to have our most upwelling via thermohaline circulation and glaciation. We then see a decline across much of the rest of the unit, of unit 3 of the lower member and within the upper member. The next trace element data we looked at was detrital input. First, we looked at titanium, which is the element associated with chlorite and other clays. We also looked at zircon, which is the element associated with detrital zircon grains. And lastly, we looked at aluminum oxide, which is the element associated with feldspars and other secondary clay minerals. So essentially what we're seeing here are elevated values across much of the lower member for aluminum oxide and zircon. And this is because we probably have increased detrital input during some of the shallower water depositional environments, along with the inclusion of these mud rip-up class of the Eureka quartzite, which serve as detrital input. We then see another small spike here in aluminum oxide at around 55 meters. This would make sense with our breccia. As we decrease sea level and subaerially expose our ramp, we'd expect the influx of detrital material to our carbonate ramp. And we're also seeing a spike in titanium here at around 60 meters. And this is because titanium is probably being swept by runoff to our carbonate ramp as we have subaerial exposure. And note that I haven't really talked much about zircon throughout the remainder of the lower member and up into the upper member. And that's because we're really seeing diminished values of zircon here, which ultimately indicates that we have far away source or lack thereof of detrital material. And lastly, the last trace element data we looked at was diagenesis. First, looking at strontium, which is this green line. Strontium has an average of 470 to 550 parts per million for carbonates deposited under normal seawater conditions. Strontium has an average value of 500 to 700 parts per million for carbonates deposited under evaporatic conditions. The Ely Springs dolomite averages just 67.1 parts per million. So why are we so reduced in our strontium here? And this is because strontium is probably lost in burial diagenesis when you have the secondary replacement of aragonite when you have the replacement of primary aragonite with secondary dolomite. Next, looking at iron. Iron has average values of 3 to 50 parts per million for carbonates deposited under normal seawater conditions. The Ely Springs dolomite averages 727 parts per million. So we're probably seeing an increase in iron because under burial diagenesis, it's probably being enriched with fluids. It's probably being, there's probably an influx of fluids that are enriched in iron that are being delivered to the Ely Springs dolomite. Manganese has an average value of 1 part per million for dolomites deposited under normal seawater conditions. It has an average of 34,000 parts per million for dolomites affected by meteoric diagenesis post-deposition. The Ely Springs dolomite has an average value of 167.8, which is much closer to this 1 part per million for carbonates deposited under normal seawater conditions. So we can assume that it probably didn't undergo much meteoric diagenesis. We're probably seeing some increase in manganese because manganese is more easily incorporated into the dolomite crystal lattice under reducing conditions. And furthermore, we probably had an increase, or under burial diagenesis, we probably had fluids increased in manganese, or it was subjected to fluids increased in manganese. So basically our diagenesis summary is telling us that the Ely Springs dolomite was subjected to burial diagenesis under reducing conditions with fluids enriched in manganese and iron while being depleted in strontium to burial diagenesis. So what does the combination of all this data tell us when we're looking at the lithology, sequence stratigraphy, trace element data, and our delta C13? What's essentially happening here with sea level and the timing of glaciation throughout the late Ordovician? Let's take a look at our conclusions from this study. The first thing we know is that the Ely Springs dolomite was deposited along this middle to inner to middle carbonate ramp depositional environment along the western margin of Laurentia. Our sequence stratigraphic data for the Ely Springs dolomite at both localities has been able to track a third order depositional cycle of glaciation. We don't see any unequivocal cool water carbonate grains, but this doesn't rule out the fact that sea surface temperatures couldn't have decreased at one point or another within the late Ordovician. We also see a diminished portion of the Hernantian isotopic carbon excursion within the Ely Springs dolomite that we see here. And we've probably lost some of those values, or some of those more enriched values, to non-deposition or erosion. We also see increased primary productivity under the influence of upwelling during the apex of glaciation here at the base of the Hernantian. Our trace element data again tells us that the Ely Springs dolomite was probably underwent burial diagenesis under reducing conditions with fluids enriched in manganese and strontium. Or I think it should be iron. And lastly, the late Ordovician glaciation was most likely constrained to this 1 million year interval of the Hernantian, with the likes of Brenchley et al. In 1994, and ultimately contrast with the hypotheses of Saltzman and Young 2005 and Pope and Steffen 2003. And we can see here all our data combined advocates for this short glacial period, where you have this increase in productivity through barium. We have an increase in detrital material as we reduce or decrease sea levels and subaerially expose our carbonate ramp. That all matches up nicely with our Hernantian carbonate excursion, or HICE, all indicating again that we would have a short glacial period of about 1 million years. So I'd like to thank my thesis advisor, Dr. Adam Woods, my extended family who cannot, or my immediate family who cannot be here today. I'd like to thank Ross for helping me out in the field, along with Danielle Forrester, who could not make it today, and my funding sources, GSA and the CSUF Geology Department. And special thank you to Sean Lloyd for letting me use his lab and almost messing stuff up, but not quite. And that's about it. Questions, concerns?